Types of metamorphism. Metamorphism, the process by which rocks undergo changes in mineralogy, texture, and sometimes chemical composition, occurs due to changes in temperature, pressure, and/or the presence of chemically active fluids. There are several types of metamorphism, each driven by different conditions and processes. These types can be broadly categorized into regional, contact, dynamic, or cataclastic, and hydrothermal metamorphism, each with its unique characteristics and geological settings. Regional metamorphism. This type of metamorphism occurs over large areas and is typically associated with the tectonic forces involved in mountain-building processes, such as continental collision or subduction. The high pressures and temperatures experienced by rocks deep within the Earth's crust cause them to undergo significant changes. Regional metamorphism often results in the development of foliation, where minerals align in a preferred orientation, giving the rock a layered appearance. Common minerals formed in regional metamorphism include micas, schists, gneisses, and amphiboles. Contact metamorphism. Contact metamorphism occurs when rocks come into contact with molten magma or hot fluids emanating from an igneous intrusion. The intense heat from the intrusion alters the surrounding rocks, causing recrystallization and the formation of new minerals. Unlike regional metamorphism, contact metamorphism typically affects a smaller area near the intrusion, resulting in a distinct metamorphic zone called an aureole. Rocks subjected to contact metamorphism often display a distinctive texture known as hornfels, characterized by a fine-grained, non-foliated structure. Dynamic or cataclastic metamorphism. Dynamic metamorphism results from the mechanical deformation of rocks along fault zones or shear zones without a significant change in temperature or pressure. The intense pressure and shear stress experienced during faulting cause the minerals within the rocks to deform, producing a fine-grained, foliated texture. This type of metamorphism is common in areas of active tectonics, such as transform plate boundaries, where rocks are subjected to high levels of stress and strain. Hydrothermal metamorphism. Hydrothermal metamorphism occurs when hot, chemically reactive fluids circulate through rocks, causing mineral alteration through dissolution and precipitation processes. These fluids are often associated with volcanic activity or deep-seated hydrothermal systems, where they can leach minerals from surrounding rocks and deposit new minerals in their place. Hydrothermal metamorphism can occur at relatively low temperatures compared to other types of metamorphism, but the presence of reactive fluids can lead to significant changes in mineralogy and texture over time. These types of metamorphism are not mutually exclusive, and rocks may undergo multiple metamorphic processes depending on the geological conditions they encounter. Additionally, the degree of metamorphism experienced by a rock depends on factors such as temperature, pressure, time, and the composition of the parent rock. Studying metamorphic rocks provides valuable insights into the geological history and tectonic processes that have shaped the Earth's crust over millions of years. What are the main reasons for the formation of types of metamorphism? The formation of different types of metamorphism is driven by a combination of geological processes and environmental conditions. These processes can be broadly categorized into thermal, pressure, and chemical factors, each of which plays a significant role in shaping the characteristics of metamorphic rocks. Here's a more detailed exploration of the main reasons for the formation of various types of metamorphism. Temperature. Temperature is a crucial factor in metamorphism as it influences the rate of chemical reactions and the stability of minerals within rocks. The heat necessary for metamorphism can come from several sources, including magmatic intrusions. Contact metamorphism occurs when rocks are subjected to high temperatures due to the intrusion of molten magma. The heat from the magma alters the mineral composition of surrounding rocks, leading to the formation of new minerals. Geothermal gradient. Regional metamorphism is primarily driven by the increase in temperature with depth within the Earth's crust, known as the geothermal gradient. As rocks are buried deeper, they experience higher temperatures, promoting recrystallization and mineralogical changes. Frictional heating. Dynamic metamorphism, occurring along fault zones or shear zones, generates heat due to the intense pressure and frictional forces during tectonic movements. This localized heating can induce metamorphic changes in the rocks without a significant increase in temperature across a large area. Pressure. Pressure, along with temperature, plays a crucial role in metamorphic processes by influencing the mineral assemblages and textures of rocks. The two main types of pressure relevant to metamorphism are confining pressure. Regional metamorphism is associated with high confining pressures resulting from the overlying weight of rocks or tectonic forces. This pressure promotes the development of foliation and alignment of minerals in preferred orientations. Directed pressure. Dynamic metamorphism involves directed pressure along fault planes or shear zones, causing deformation and shearing of rocks. This pressure results in the development of foliated textures and can lead to the formation of mylanites and cataclysmites. Chemical activity. Chemical reactions between minerals and fluids play a crucial role in metamorphism, leading to the alteration of mineral compositions and the formation of new minerals. Key factors contributing to chemical changes during metamorphism include hydrothermal fluids. Hydrothermal metamorphism occurs when hot, chemically active fluids circulate through rocks, dissolving and precipitating minerals. These fluids can alter the mineralogy of rocks by introducing new elements and facilitating recrystallization. Fluid-rock interaction. Interaction between fluids and rocks during metamorphism can lead to the exchange of ions between minerals, promoting recrystallization and the formation of metamorphic minerals. Overall, the formation of different types of metamorphism is a complex interplay of temperature, pressure, and chemical activity, with each type characterized by distinct geological settings and processes. Understanding these factors is essential for unraveling the geological history of rocks and interpreting the tectonic processes that have shaped the Earth's crust over time. What is the importance of types of metamorphism in the formation of different rock types? The various types of metamorphism play a fundamental role in the formation of different rock types, contributing to the diversity and complexity of Earth's crust. Understanding the importance of metamorphism in rock formation involves recognizing how each type of metamorphism influences the mineralogy, texture, and overall characteristics of rocks. Here's a breakdown of the significance of different types of metamorphism in the formation of various rock types. Regional metamorphism. Formation of foliated rocks. Regional metamorphism, occurring over large areas due to tectonic forces, leads to the development of foliated rocks such as schists, gneisses, and phyllites. The alignment of minerals in preferred orientations results in distinct layering or foliation, which is characteristic of these rock types. Formation of high-grade metamorphic rocks. Regional metamorphism often occurs at significant depths within the Earth's crust, where high temperatures and pressures prevail. This environment favors the transformation of pre-existing rocks into high-grade metamorphic rocks, such as granulites and eclogites, characterized by the presence of minerals stable at high-pressure conditions. Contact metamorphism. Formation of non-foliated rocks. Contact metamorphism, induced by the heat from magmatic intrusions, results in the formation of non-foliated rocks such as hornfells. These rocks typically lack the layering or alignment of minerals seen in foliated rocks and exhibit a uniform, fine-grained texture. Formation of metasomatic rocks. Contact metamorphism involves the interaction of rocks with hot fluids derived from the intruding magma. This process can lead to metasomatic alteration, where minerals are dissolved and replaced by new minerals deposited from the fluid. Examples include the formation of marble from limestone and the development of skarns in carbonate-rich rocks. Dynamic or cataclastic metamorphism. Formation of mylanites and cataclysmites. Dynamic metamorphism, occurring along fault zones or shear zones, results in intense deformation and shearing of rocks. This leads to the formation of mylanites and cataclysmites, characterized by finely fragmented and sheared rock fragments, often exhibiting a foliated texture. Localized metamorphic effects. Dynamic metamorphism typically affects narrow zones along fault planes, resulting in localized metamorphic effects within the broader geological context. These effects can include fault brecciation, mineral lineations, and localized mineral recrystallization. Hydrothermal metamorphism. Alteration of rocks by fluids. Hydrothermal metamorphism involves the circulation of hot, chemically reactive fluids through rocks, leading to alteration and mineral replacement. This process can result in the formation of economically important ore deposits, such as sulfide deposits in hydrothermal veins and deposits of gold and other precious metals. Formation of vein deposits. Hydrothermal fluids can precipitate minerals in open spaces within rocks, leading to the formation of vein deposits. Examples include quartz veins containing gold or silver, as well as sulfide veins rich in base metals like lead, zinc, and copper. In summary, the various types of metamorphism are integral to the formation of different rock types, contributing to the diverse array of rocks found within the Earth's crust. By understanding the processes and conditions associated with each type of metamorphism, geologists can unravel the geological history of rocks and interpret the tectonic and environmental forces that have shaped Earth's surface over geological timescales.